All right. Hello, everyone. Happy Thursday around the world. Maybe Friday if you're based over in Australia or New Zealand. I'm happy to be here with everyone today. My name is Heather Grant. I am one of the community admins here at the Maintenance Community by Upkeep. Thank you once again for making the time to join us here today. If you are not already a member of the maintenance community on Slack, we would love to have you join us. I will add the sign up link in the chat in just a moment. Today, we have Evan Zabowski joining for a presentation on getting started for oil cleanliness. I know it's going to be a really interesting presentation. I got a little sneak preview this week, so I'm excited to sit and hear Evan speak to us today. And I'll let him introduce himself, tell us a little bit more about himself and what we'll hear in just a moment. The recording from our session today will be available in the maintenance community on Slack tomorrow, along with a copy of the slides that you see here today. And it actually will be available right at this link once we end recording. Evan is also available in the Slack group, so please feel free to share either the recording of this webinar or the invitation to Slack with any friends, colleagues, or anyone else you know who would benefit from some of Evan's expertise. My last piece of housekeeping, and then we will go ahead and get started with our main event. You'll notice that your cameras and microphones are not turned on today. So what you'll do if you have any questions for Evan as we go throughout the presentation is please use that chat feature on the right-hand side of your screen. As I said, please feel free to drop the questions in there as we go throughout the presentation, and we should have a few minutes at the end of our hour to go through anything that comes up. I think that's it from me. Thank you everyone for being here, and thank you, Evan, for making the time to join us. I will turn it over to you to get started.
Well, thank you. Yes, so I'm Evan Zabowski. I am the Senior Technical Advisor here at Test Oil. We are a commercial oil analysis laboratory, and what I do there is mostly training like this. So I do train both on and off site and sometimes do some consulting work. So I'm always looking for ways to share some knowledge and help people do things a little bit better. Today's topic is a part one. There will be a part two about oil cleanliness. And essentially, if you think about oil cleanliness from purchase all the way through to use, I consider that there's essentially 5 steps that you have to think about. Initial delivery. First thing we must realize, or at least acknowledge, is that new oil is not clean oil. And we should probably set a target cleanliness for how clean we want it to be. And that'll be the topic of today's presentation. After that, we consider storage. Once we've taken delivery of it, we must store it. And in this case, we have to look for ways to prevent any contamination and possibly avail ourselves of some ways of filtering it while it's in storage. After that, we need to take it out of storage, carry it towards the machine, pump it directly into the machine, whatever it might be. And again, the same considerations come up. How do we prevent contamination? Are there any other opportunities we have for filtering it? Once it's in the machine, we have to discuss exclusion. That would be essentially, we're going to think about breathers, right? How do you keep contamination from getting in? How do you keep it from getting any dirtier? The last step is called conditioning, which is a fancy way of saying filtration, because this involves removal of particulate, water, varnish, insolubles, whatever you might want to consider, but different ways to condition the lubricant. And really what we're going for on that 5th and final step is, if we have not had yet an ability to filter the oil in any of the previous steps, here's where the rubber meets the pavement, and we're going to have to do it. So we will work again back towards that target cleanliness. That last step will be the main discussion point of part 2. But anyways, before we get started on step 1, what is the topic of today's presentation, let me give you a little bit of a preamble. So since I'm going to be using the term a lot, let me define it. What is a micron? A micron is a millionth of a meter, or what some people call a micrometer. It's about 0.00004 thou of an inch. So 4 zeros and a 4. It's a very, very small measurement. To give you perspective on a micron, common examples are the cross-section diameter of hair. Human hair is about 75, 80 microns typically. If you cut that in half and go to 40 microns, that is usually considered to be the lower limit of detection. The unaided, naked eye, black speck, white sheet of paper. Can you even see the speck? It's got to be about 40 microns. Now, considering that, let's go a little bit smaller. What if we talk about 25 microns? Now, if you notice on this list, that's the same size as a white blood cell. But keep looking down the list and you'll also see red blood cells. They're about 8 microns. Those are two numbers you're going to want to hold in your head for a couple of minutes here. 25 microns for a white blood cell, 8 microns for a red blood cell. I'm sure we've all had blood on our hands. We've had a cut or something like that. Never once did you, look at your finger and go, oh my goodness, look how polka dotted my blood is, right? We can't see the white blood cells any better than we can see the individual red blood cells. And since there's a lot more red than there is white, we perceive our blood to be, red. So considering that those are some important micron sizes, one of the best questions you can ask yourself of any system is, well, how clean does it need to be? And that's going to lead to the question of what is the most damaging size of particle. And I'll share with you, there's an interesting automotive paper, and it concluded that particles between 2 and 22 microns were the most important particle sizes to control to mitigate engine wear. But that's just engines, right? That doesn't necessarily translate to all other types of machines. So we have to ask ourselves, is this usable information? And one of the most famous pieces of information along that sort of thought is something that you may have seen before. It's called the McPherson curve. And the McPherson curve is just a general plot of data from a very old study. If you start at the very far right-hand side of this graphic, what you're noticing is micron sizes and a level of filtration. The left-hand axis is a number of millions of cycles of a bearing, whereby 50% of the population survived to that point. So basically, we're looking at a plot of, well, how good of filtration has what impact on the life cycle of a bearing. So starting at the very far right of this graphic, you'll see that at 40 microns of filtration, so filtering particles that you can see, we get about 2 million cycles as the average life of 50% of the bearings. If you could go all the way down to 25 microns, though, the size of white blood cells, you will see that you can increase that to 3 million cycles, a 50% increase in the life of a bearing. That's pretty substantial. But as you can tell from the curve, the best is yet to come. If we can filter it all the way to 8 microns, the size of red blood cells, we will double it again to 6 million cycles, so 3 times life extension. Now, this starts to seem pretty impressive to most people, but again, looking at the curve, there's even more to come. If you could filter it all the way down to 3 microns, you will see that you will double it yet again to about 12 million cycles. And where it gets really interesting is, what if you filter it all the way down to 1 micron? You only get about 400,000 more cycles as the average life of the bearing, and you can see that it doesn't really have that significant of an impact. So it really points out this sweet spot in terms of filtration, that changing the filtration from 40 microns to 25 microns didn't have that much of an effect. In fact, even changing it from 25 microns to 8 microns still did not have that much of an effect. But once we went below 8 microns, until we reached about 3 microns, we saw the biggest bang for our buck, the best return on investment, whatever way you want to phrase that, in that range. And so to help us understand why the McPherson curve is so interesting and what is the important takeaway from this, let me show you one more paper. This paper was published in STLE's magazine, and it was specific to hydraulic systems. But it said the critical particle size to control must be 1 to 2 microns. But it used a very important word in that statement. It says based on these clearances. And you're wondering, why does 1 to 5 microns matter to the clearances within the hydraulic system? Well, if you take a look at an example here, it's not the example from the paper, it's just of a journal bearing. So you see a shaft inside of a journal. If the clearances on the journal vary from 1 micron at the closest point of near contact where the hydrodynamic film exists to the opposite side of the shaft where there'd be the greatest clearance, and those worked out to be 1 micron at the tight clearance and 5 micron at the large clearance, you could start to understand why any particle larger than clearance wouldn't cause any damage, and any particle smaller than clearance also wouldn't cause any damage. And really, that's what we're getting at. That's the important word here. The most damaging size of particle is a clearance-sized particle, because particles larger than clearance can't get between the two surfaces and cause any of the abrasive wear. Particles smaller than clearances will just zip through without touching anything. So it's the particles that are at or near the dynamic clearances within a piece of equipment that are going to be the most damaging. Now, of course, this would beg the question, I don't know my clearances, so how would I find that out? So I reproduced a table from ASME here that lists very common clearances in a lot of different types of machine parts. What you're going to see is that within that 1 to 5 micron range, you're going to cover most of the ranges listed in this table. So it shows you why the McPherson curve shows us and proves to us that filtering definitely less than 10 microns, maybe less than 8 or even less than 6 microns, is really where we start to have an impact on the reduction of wear. Now, just to show you why we focus so much on abrasive wear or even adhesive wear, I'll show you yet one more study here as part of my preamble. This one's from Dr. Rabinowitz, and he was the one who studied failures of bearings, and he didn't call them failures. He called them a loss of usefulness, meaning that they simply didn't function the way they were intended to function. So they didn't necessarily catastrophically fail, but they stopped working the way they should. What he did was he attributed that most of that loss of usefulness was due to something he called surface deterioration, which is kind of a big mouthful for saying wear. When you're wondering why he didn't use the term wear, is because when he classified what caused surface deterioration, he said that most of it wasn't chemical wear, it was actually physical wear. So he called chemical wear corrosion and he called physical wear just plain wear. But once he broke down what was causing the wear, the physical wear, as you can see, abrasive wear and adhesive wear were the two biggest contributors. And of abrasive wear, the biggest contributor by far was three-body abrasive wear, which is particulate in between two surfaces in relative motion. Two-body abrasive wear is just the two surfaces abrading against each other, kind of like sandpaper and wood. So the point being that this is kind of like the, if you use the Pareto principle, this is the low-hanging fruit. This is the 80% of our problems can be resolved with 20% of the effort. If we can get rid of the particulate that are at or near clearances, we will get rid of one of the largest slices of, backing ourselves through this whole graphic here, of the largest slice of the largest slice of the largest slice. And just to show it to you one more time from yet another study, a very popular one, this one was done in Canada. It attributed about $5 billion a year in industry was being lost due to friction and wear. When they classified where that friction and wear were coming from, on the wear side of it, you can see where abrasive wear, adhesive wear, and even erosive wear all were the three biggest slices of the pie. And if you add up those three slices, you'll get 82% of this pie. So that's how you get that statement, 82% of wear is particle induced. It just goes to show no matter how many different ways we've studied this, we know particulate or contamination leads to shortened equipment life. We also know that it's the clearance size particles within that contamination levels that are going to give us the most grief. So we need a way of identifying and therefore excluding or removing these particles if we want the maximum life for our components. Now, on that note, just a quick commentary here. Where does all this particulate that we're going to talk about come from? Well, there's essentially three different sources. There has a source that we call built-in, and that means both figuratively built into the processes we use to maintain the equipment, but also means literally built in, as in during assembly, commissioning, or installation. We have external contaminants, which enter because they can come through any openings, fill caps, tank lids, inspection ports, breathers, whatever it might be. And many of them are environmental. Some of them may be related to the process the machine is performing. And last but not least, the third category is what we call internal, meaning the particulate was generated on the inside. And this is often from wear mechanisms, so it could be from abrasive wear, adhesive wear, could be from something just like corrosion. But it also comes from other aspects like fluid degradation, where the fluid itself may break down or mix with something else and create a precipitate or a fallout that will contaminate the system. So if you're a little bit curious, just because I knew I was including the slides, I've broken down each of those three and given some examples. So on the built-in side, like I said, anything that's figuratively built into the processes that we use to maintain it. Simply pulling out a dipstick to check the level may introduce contamination because you're opening up the system, exposing it to the atmosphere. The dipstick is wet with oil, you're exposing it to the atmosphere, and then you're maybe just reinserting it without wiping it off. There's a potential that you've introduced a small amount of contaminants. But if you've got something like a fill cap that needs a funnel, and you're now using a funnel to fill the system, the funnel has a much greater surface area than the dipstick. And if the funnel's been left outside, it will be a giant dirt magnet. And as you pour new oil in there, you're going to be introducing contamination. So that's what we mean by the figuratively built into the processes. The literally built in is, pipe scale and corrosion of metal parts. Even from cutting new threads or welding material together, you can create all sorts of particulate on the inside as you construct or install and otherwise commission a brand new piece of equipment. So generally, these type of particulate, we know that we can remove them safely quite ahead of time by flushing. And we're going to talk more about flushing in a bit. The external contaminants, these are the ones, like I said, generally fall into two categories. Those related to what the machine's doing. So if the machine's cutting, grinding, milling, anything like this, it'll be creating a lot of dust or particulate in the atmosphere. Versus there's environmental considerations. And environmental, can also mean things like humidity, but from the particulate side, it could mean dust from wind, it could be pollen because it's a change of the seasons, all kinds of things like that. They are particulate, they're small enough, they can enter through and get into the system, they will be abrasive. On that last category of internal, I've given you a few examples here. Pretty much everything on the left-hand side are different physical wear mechanisms. But there are a couple at the bottom that are the very things that we install to try and minimize contamination or otherwise handle contamination that can actually contribute contaminants themselves to a lesser degree. So things like hoses, filters, and even seals, as they abrade or fail, they will release some particulate in the form of, generally fibers and whatnot. On the right-hand side, though, is an interesting list of things that are created because the fluid degrades. So there's the obvious sort of gels and precipitates that form when you have incompatibilities or additive dropout from mixing of different fluids or contaminant in the fluid. But then there's unique ones like carbon. Carbon is created through thermal events. And two of the most common types of thermal events that create carbon particles within the oil are microdieseling or electrostatic spark discharge, otherwise known as ESD. Those produce some very, very small carbon particles that generally, to most people, only look like they're darkening the fluid and don't look like they're a big deal, but they can build and agglomerate to be clearance-sized particles and therefore would be quite abrasive. So with that being said, enough preamble, let's get into the actual heart of the presentation here, talk about what was that step one again? It was the delivery. We know when we take delivery of a lubricant that it is not clean. New oil is not clean oil. You'll hear me say that a couple of times. And we need to come to that realization, but then we need to decide, well, how clean should it be? So to help us understand the statement, new oil is not clean oil, let's look to one of the most widely cited standards in the industry for how clean lubricant should be prior to use. Now, this one was put together by AGMA, so it is written from a gear oil perspective. So it's not to say that it generally does apply to any other types of machines. However, because it's one of the few documented standards, people tend to apply it to everything. But if you read this statement here, it says must be free of visible suspended particulate. So think about that, visible, right? As I said before, to see it with your own eye, to actually be able to perceive a particle, it's generally considered to be around 40 microns or larger before we can see it. Well, that's not really the damaging size particle. Most clearances are way smaller than 40 microns. So this is not good criteria for determining how clean fluid should be. In fact, if you saw visible particulate, there's a better than not chance that that particulate wouldn't even cause any damage, wouldn't get between the machine parts, would settle out, and wouldn't be an issue. So with a standard like this, you start to understand why we can make a statement like new oil is not clean oil. But on the other hand, it's only one. So let me show you a second one just to back me up a little bit more. This is API 614. This is a commonly cited standard within industry because it's used for commissioning new equipment or sometimes recommissioning recently overhauled or rebuilt equipment. And if you read through this, it's got a few things that it has to say about what a flush looks like to properly flush a system to make sure it's clean enough prior to use. And as you begin to read it, I think you can pick this apart pretty quickly. First and foremost, it says you must perform a flush, and then it says it's a 1 hour flush. Well, I don't know if you have experience with flushing, but I'll tell you this. Most flushes I participate on take at least 1 day, let alone 1 hour. So 1 hour is an incredibly short time frame to try and do a flush on any size of system. But it says do 1 hour worth of flush, and it says to do it at design flow rate. Well, what that is implying is that you don't need secondary pumps. You're going to use the system's pumps to circulate the fluid. Well, system pumps typically don't flow that quickly, right? They're only meant to handle a low flow rate because they're just trying to circulate the oil fast enough to lubricate and remove the heat and whatever else they're doing. So my issue with that, and I'll get on into this on the next slide, is that system pumps tend to run at a very low flow rate that ends up usually within the laminar region. So if you're not familiar with what laminar flow is, I'll explain that on the next slide. But for those that understand, you start to see where I'm picking this apart. It's not turbulent. It's not going to be having a good cleaning effect. Now, to top this all off, it says this 1 hour flush at a low flow rate is to yield clean 100 mesh screens. If you're not familiar with mesh sizes, I've got a note there at the bottom that says 100 mesh is approximately 149 microns. Those are some pretty big holes. I mean, it's better than bug screen on your screen door, but it's not a very good screen. So we're talking about yielding clean screens as a way of confirming that the flush is done. The flush has performed its duty. So the quote I have within the slide here is the direct quote from API 614. And as you can read, it says, to further verify the cleanliness, you install 2 to 6 of these screens throughout the system. Doesn't really give a lot of guidance as to where the screens go. But it says at the conclusion of the flush, after the 1 hour, you will pull the screens out, you will look at them, and you will assess them both visually and physically. And so it says, if you read the rest of the quote, that it's considered clean if you don't see anything on the screens and if you can't feel them with your fingers. Well, think about that, right? Touch is very subjective. I mean, never mind, just using human eye as a way of checking for the presence of something, right? If it's pretty small, you might disagree, depending on how good your eyesight is or how good the lighting is. But touch is very subjective, right? Some of us have, thick calluses on our fingers from working so hard, and some of us, like me, we don't tend to get calluses from typing too much, so much softer hands. So I don't know if they're necessarily more or less sensitive. It's a hard judgment. So you can start to see this standard is not really well written so that it's universal, that all of us would say, yes, that system is clean enough versus maybe it isn't. So just to hit on that other point, why am I harping about the laminar flow? Because that's one of my biggest concerns. Both the duration and the flow rate of this flush dictate it's not going to work very well. And here's what I'm getting at. When we talk about flow through, in general, piping, we talk about the flow and we will describe the flow using terms like laminar or turbulent. And what laminar flow means is that essentially if you think about the flow going through the pipe, it's in layers. So it's kind of like taking a deck of cards, and if you consider the entire height of the deck of cards and you go, okay, if you push really hard on the card that's in the middle of the deck, how much do the other cards move? And you would say to yourself, well, the cards that are right next to the card you're pushing will definitely move because there's friction against them. And then you go, well, how much do the next layer of cards out move? And you go, well, they'll move a little bit too because there's friction on that. But as each layer of cards you move away from the center, the friction is just a little bit less and less and less and less until the movement on that outer set of cards holding the deck top and bottom is not moving at all, right? You can push that center card along and you're not really moving the cards at the top and bottom of the deck. And when you think fluid as being laminar flow, that's kind of the same premise that we're going here. You can see the graphic that the fluid down the center of the pipe, and in this case, the layers aren't stacked because they're going to be circular, but the flow will go through the very center of the pipe quite nicely. But as you get closer and closer to the walls of the piping, the fluid's going to move less and less because it'll have less friction against itself. And there's going to be almost no movement, relatively speaking, towards the walls of the piping. So my point is, how do you expect that to pick up particulate and anything else within the system? So what we like to consider for flushing is we like to talk about turbulent flow, because this means that basically there's not layers and they're just tumbling over each other as they flow through. So they will have an ability to pick up particles and carry them through to the screens, to the filters, to whatever you've got. So some quick terminology here. When we're describing flow, we often refer to a characteristic known as the Reynolds number. And when the Reynolds number is being calculated for the viscosity, temperature, and all these kind of considerations of the fluid in whatever piping it may be in, This Reynolds number is generally considered to have laminar flow at any Reynolds number less than about 2300, depending on the textbook you read it from. And we're pretty sure that we consider it to be turbulent flow if the Reynolds number works out to be higher than 4000. To give you a frame of reference, general best practices for flushing require a Reynolds number of 25,000 or higher. So my point being, going back to that earlier comment about API 614, design flow rate is nowhere near turbulent, and nowhere near, even if it was even slightly turbulent, it's not going to be the degree of turbulence that's generally considered good cleaning. And I guess the best example I can give you is, think of it this way. Whether you go to the car wash or you go to your garden hose, if you consider that the flow rate out of either is 5 gallons per minute, what changes is the velocity. And you think, what would you rather use to clean your car if it was muddy? A pressure washer or a garden hose? You're going to get the same 5 gallons per minute water. So it's not about the flow rate, it's about the velocity, right? And that's what we're really going for. And that's the big factor that can change a Reynolds number, is the velocity through the piping. So, think of it that way if it helps. But anyways, as I stated way back at the beginning, I said new oil is not clean oil. That is the big statement I need to keep reiterating until we totally understand that. So here's how I can try and prove it to you. If we take a look at the typical new oil deliveries, now this could be in plastic, this could be in steel, this could be in quart jugs, 5-gallon pails, 55-gallon drums, 250-gallon totes, bulk delivery. It really doesn't matter what type of container, or even if there's a container, and it doesn't matter the volume. This statement still holds fairly true, that the typical cleanliness of new oil, so virgin oil before use, is around an ISO code of 2019-16, and I'll always, suffix that with give or take a code, but 2019-16, and my point is that ranges typically to about 8 to 32 times dirtier than any OEM will recommend as the cleanliness for the lubricant in the running system. Now, I know, generally speaking, when I teach groups about this, as soon as I say an ISO code of 2019-16, I've lost people. I know that there's some people who don't understand ISO codes. I also know that there's a lot of people out there who think they understand ISO codes, but don't really have a good way of explaining it to somebody else and making it into a tangible comparison. Most people who think they understand it just say, well, relatively speaking, if it goes up a code, it's twice as dirty. And I go, fair enough. But how do you know how dirty it is to begin with, right? Twice as dirty as something doesn't tell me anything if I don't know how dirty it was to start. So this is the other aspect of the presentation I want to make sure we get clear before we set a target cleanliness, is we need to understand ISO codes. So with that thought in mind, hold this thought about the 8 to 32 times cleaner. Let's understand ISO codes first. So when we do a particle count, whether this is done in the lab or done with a portable particle counter, particle counting is typically reported using an ISO coding system. And the ISO coding system takes your particle count, and this is an important detail, per milliliter. So there's a number of particles per milliliter of the lubricant. And you go, well, how big is a milliliter? It's a cubic centimeter. You go, how big is a cubic centimeter? It's about the volume of the tip of your pinky from the last knuckle. It is not a big volume. So you go, okay, we're counting hundreds, thousands, maybe even 100,000 particles in that tiny, tiny volume. It's just a count. So how do we make it tangible? How do we make it a number we can work with? So what we do is, when we count those particles per milliliter, we group them into 3 categories: greater than 4, greater than 6, and greater than 14 micron. So what I'm hoping you realize is that every one of those categories is greater than. So if I count a particle as greater than 14 microns, I will also count it in the category of being greater than 6. And all those particles I will also count in the category of being greater than 4. Right? That's what I'm hoping we realize, is that there's a lot of overlap to these categories. So when you consider the particle count as a count, it's just a number of particles per milliliter in these 3 categories. What we then do typically is code them, and this is where the ISO code comes in. And we code them in that same order: 4, 6, and 14 microns. So what you're going to get as a reported value, like I just gave you the example of 2019-16, is 3 different ISO codes. And this is where I think a lot of people start to get confused, because they're like 20, 19, and 16 what? Right? It's not pounds, it's not kilograms, it's not a mass, it's not a volume, it's nothing, it's a number. So how do we understand the numbers? So with that, let me show you how we get to the numbers, and then I'll show you how to understand the numbers. So how do we get to the numbers is going to be the left-hand table here. On the right-hand side are just 2 different examples. I'll go through the top one just to give you a chance to see it. But in the left-hand table, we've got a list of ISO codes. That's the left-hand column. To the right, you will see the range of those codes for how many particles per milliliter fit within that range. So let me show you something that, again, I know a lot of people know this already, but let's make sure we cover this. Let me show you the pattern to the table, because there's something that a lot of people do miss. So starting at the 5th line from the bottom, where it says ISO code of 10, take a look at that line there, and it says an ISO code of 10 is a code you would assign to any particle count that has between 5 and 10 particles per milliliter. Now, if you just go up a line to ISO code 11, it says you have a particle count of between 10 and 20 particles. And if you go up to the next line, you'll see that it says between 20 and 40. Most people are pretty quick to notice this pattern of doubling. And that's where you get that statement: if the ISO code goes up by 1, the particle count doubles. Now, that being said, what some people don't necessarily pay as much attention to is that the range also doubles. Right? The range between 5 and 10 particles is simply 5. The range between 10 and 20 is now 10. The range between 20 and 40 jumps to 20. As we go up and up and up the table, the ranges get wider, wider, wider. So they start to get very, very inclusive. And that's going to become an important detail when I go through the example in the next slide. But looking at this example here on this slide, the top example, let's see how they arrived at the codes. Right? The particle count for the greater than 4 micron value says it's 151,773 particles. That is between 80 and 160,000 particles per milliliter, which is an ISO code of 24. So you can see between the 2 tables, there's a little line. You can follow where the code came from, which line it came from. So a particle count like that gets assigned an ISO code of 24. If you come down to the next line there, where it says it's got the 38,000 and change, that's between 20,000 and 40,000. That's an ISO code of 22. And if you look at the last one, the greater than 14 value, that's 3,000 and change. Well, that's between 3,000 and 5,000, or 2,500, sorry, and 5,000. That's an ISO code of 19. So in the end, that particle count in the top table, which was 151,773 and so on and so forth, we simplify that into a statement of 24, 22, 19. Now, I know when I teach this live that, generally speaking, if I point this out, most people laugh. I said all we did was we took one set of numbers on the left-hand side of the slide. It was a set of numbers we had no hope of understanding it, and we've converted it to a new set of numbers we still don't understand, right? Because like I said, 24, 22, 19, what? Right? It's not anything. So here's how I think I can make a little bit more sense of the ISO codes. Using this table that you see here, let's do some coding of some actual results. So notice on this slide here, I've got 3 examples: first, second, and third sample. Let's code them. So I'll show you how we code the first sample, and then if you really want to, you can do the second and third yourselves. But anyways, looking at the particle count here of the first sample, greater than 4 microns is 1,357 particles. That is between 1,300 and 2,500. That is an ISO code of 18. So you would fill in 18. Next number there is 361. That's between 320 and 640. That is an ISO code of 16. So filling in our little chart here, that becomes 16. And the last number, 42, is between 40 and 80, which represents an ISO code of 13. So we fill that in as 13. So the first sample would work out to be an 18, 16, 13 to represent the particle count that you see below it. But here's a more interesting question. If I have you look at the 3 particle counts, first, second, and third sample, and asked you what was happening to the particle counts I think most people would be pretty quick to notice that they're increasing. But now, if I ask you, are they increasing a lot or just increasing a little, we get a variety of answers, right? Some people might look at it and say, well, it's gone up by hundreds, if not, almost 1,000. That seems like a lot, and they would say it's a lot. And other people who might be familiar with higher particle counts than this would look at that and go, oh, a few hundred particles here or there, who cares? It's not very much. It becomes subjective again. So how do we know if it is really a little or a lot? Well, the interesting thing is, if we looked at the ISO codes for these three samples, we'd have a better answer. Now, I showed you how we got the first one. Here's all the others. They all work out to be 18, 16, 13. So if I show you three particle counts and tell you that all three have an ISO code of 18, 16, 13, what do we all now hopefully agree on is happening to the particle counts? Nothing. They're not increasing. They're within the same range. And that is the important point that I made earlier about the range is getting wider, wider, wider. They become more inclusive. And that is kind of the point of the ISO system, that once numbers get particularly high, a few hundred, a few thousand particles here or there doesn't really make much of a difference. And therefore, we don't need to nitpick and say this particle count's going up. No, it's all within the same ISO code. So that's kind of, helping us understand to a degree, at least, what the ISO coding system is for. But we still don't know if 18, 16, 13 is clean or dirty. So to help us understand that, let me show you this neat study that Caterpillar came up with, and it relates to all three of these being 18, 16, 13. What Caterpillar concluded was if you took an entire drum, 55 gallons, of oil and removed all the contaminants from it of an 18, 16, 13 particle count for the whole drum, you would total about a half a teaspoon of debris. So think about that for a second. That is essentially the size of one crushed aspirin, right? It's not a very big amount of particulate, but it's spread throughout the system. Would take an oil that was essentially at zero particulate all the way up to an 18, 16, 13 particle count. Now, saying what I said earlier about the particle count doubling every time the ISO code goes up by 1, my comment before that was that new oil was 20, 19, 16, give or take a code. So 20, 19, 16 is 2, if not 3 codes higher than 18, 16, 13, right? It's 2 codes higher in the first category, 3 codes higher in the second and the third category. So if 1 code doubles the particle count, 2 codes double it again, so 4 times higher. So if you take 4 times a half a teaspoon, what we're essentially able to say, to put it in tangible terms here, new oil contains roughly 4 times as much particulate as a half a teaspoon, which works out to be, well, 2 teaspoons. So there's about 2 teaspoons of debris minimum in every drum of brand new fluid. That's what 20, 19, 16 would equate to as a tangible amount. You could hold in your hands and say, this is how much dirt's in the system. Now, like I said, the other 2 codes, the 6 and the 14 micron codes, were 3 codes higher, so that would double again. So that'd be 8 times higher, which 8 times a half a teaspoon is now 4 teaspoons. So roughly speaking, we're talking about 2 to 4 teaspoons of debris in every 55-gallon drum. So hopefully that helps you understand a little bit better what ISO codes are all about and gives you an idea how to make an ISO code a bit more tangible into, if I'm looking at this oil, how much dirt is there really in there at this particle count? So just to make sure I make this point really, really clear, let me show you an example. On the left, we have 20, 19, 16 new oil, and that's what a small volume of it would look like under a microscope. On the right, though, we've got used engine oil. Now, if I told you used engine oil was dirty, you probably wouldn't think you're learning much because you would have said, I already knew that. What I'm trying to show you is mathematically how much dirtier it is. So it is about 3 ISO codes higher. It's a 24, 22, 19. So we look at that, or sorry, 23, 22, 19. I'm remembering the previous example. But that is 3 codes higher than 20, 19, 16. So that's where you get the statement at the bottom that it is 8 times dirtier after it's been used. Now, thinking about this, you knew beforehand used engine oil is dirty. I'm giving you a mathematical way of identifying, well, how much dirtier is that actually. Now consider this. Imagine you have a running hydraulic system and you go to your best container that you've got in your lube room. You know, the newest drum of oil, the one that's been not even opened yet, it hasn't had a chance to contaminate with the atmosphere, it's been stored properly, it's clean on the outside because you've got good housekeeping practices. No matter how many things you can think of that are right about this drum, no matter how many things you can think of that would indicate the drum is not any further contaminated than the day you took initial delivery of it, this is my point. It is still going to be 2019-16, and you're about to pour it into a running hydraulic system, which is probably 3, if not 4 ISO codes cleaner. So if you pour it into a system that's running at 16, 15, 12, you are shocking your system with oil that is about 16 times dirtier before it's been used than what the system wants. So this takes us all the way back to my statement before when I said 2019-16 is roughly 8 to 32 times dirtier than most OEMs would recommend. So how did I get that? It's about 3 to 5 ISO codes higher than most OEM recommendations. So that being said, I know many of us don't always get an OEM recommendation, or sometimes we don't want to use the OEM recommendation, we want to have our own. So the second part of this presentation was, let's set our own target cleanliness, right? Is 16, 15, 12 clean enough for what we're doing? Who knows? How do we find out? So let me give you a hypothetical system that we'll use as the example to round off the presentation. We're going to consider a system that uses a variable piston pump. It has a servo valve in there, and we're lubricating some journal bearings. So you see all that's listed on the slide here. One other variable we need is it's going to operate at over 3,000 psi. So what we do is from this much information, we can use tables like this one. And now I've reproduced this from Hypro filtration. And one of the reasons I like Hypro's chart is it has filter information on it. So you'll see how that comes into play in a little bit. So how do we do this? Well, if I bring up my laser pointer here just to make sure you see what I'm seeing, I said there was a variable piston pump. That's right here. I said the system operates at over 3,000 psi. That's this column right here. So for a variable piston pump operating at over 3,000 psi, the recommended particle count or cleanliness that I need is 16, 14, 12. Now I also said it had a servo valve, which is right down here. And for the recommended pressure, or the pressure that we stated, the recommended cleanliness is 15, 13, 10. And we also said there were some high-speed journal bearings in there. So we look up journal bearings right here, high speed. We look at 3,000. There's no information. We back ourselves up till we actually get some information, and lo and behold, 17, 15, 12. So in quick summary, based on what we looked up from these tables, we see that these are the recommended cleanlinesses for each of the individual components within the system. And here's your important takeaway. You don't set the cleanliness of the system based on the type of machine, right? People often ask me that question, what should be the target for my gearboxes compared to what should be the target for my compressors? And they often show some confusion when I say, well, they should be the same. And they go, well, why? You know, compressor has a filtration system. Compressors are generally known to run clean. Gearboxes, on the other hand, don't always have filtration systems on them. They're known to be open to the atmosphere, and they're frequently accepted as being dirtier. My point is, both of them have bearings in them, rolling element bearings with very similar clearances. So why would you not, considering that they have near identical bearings with near identical clearances, why wouldn't you be targeting the same size of particles? Why wouldn't you need the same cleanliness of fluid in both types of systems? So this example shows us that, yes, if we go through the parts that are actually lubricated and we see what the recommended cleanlinesses are going to be, when we find the one with the lowest cleanliness, so in our case with this particular example, it's the servo valve at 15, 13, 10. So our recommendation then becomes, because that is the overall lowest result, if it's clean enough for the servo valve, essentially it's clean enough for the journal bearings, and it's definitely clean enough for the variable piston pump, that is the recommended target for this system. Now, as I mentioned, I do like the Hypro chart for a reason, because the Hypro chart, if I just quickly go back to it for a second, coming down to the bottom again, just to remind you where I'm looking here. If I look at servo valve, come over here to 15, 13, 10, but right beside it, it says the recommended filtration to achieve a 151310 is either a 5 micron beta 1000 filter or a 3 micron beta 200 filter. Now, why I really like this piece of information, if I come back to this, is that if I know my existing filtration is, whatever it might be, 8 microns, 12 microns, 25 microns, who knows where it is, that target will be very, very difficult to achieve. So I like the HiPro chart just because it acts like a bit of a check, right? It's one thing to come up with a target. It's another one to come up with a realistic target. And I shouldn't set targets I will never achieve or will have great difficulty achieving without knowing what I'm up against. So I like that additional filter information just from that perspective, that in our hypothetical system, we know that we're going to need at least 5 micron filtration if we have any hope of getting the particle count stable at 151310 or better. Now, the interesting side of this whole discussion is, as the title of the presentation was, how to set a cleanliness target. But a lot of people don't necessarily want a target. They want a limit. And targets and limit are not the same thing. And the joking analogy that I have for you is if you're driving on a road and the sign on the side of the road says something about 55 on it, right? What are the words right below it, right? The words say speed limit. And you go, okay, 55 miles per hour. You go, do you get a ticket for going 54? No. 53? No. 50? Nah. How about 45? Probably even not then. But 40 miles an hour. You go less than 40 miles an hour on a 55 mile an hour road, you could get a ticket for going too slow, for obstructing traffic. You go, okay, fair enough. But do you get a ticket for going 56, 57, 58 even? Nah. 60? No. 65? Probably not even at 65. But you hit 70, and all of a sudden, yes, you could easily get pulled over and get a ticket for going 70 in a 55 zone. So you start to realize that we apply the term speed limit as 55 is the limit. It isn't. It's not the limit going up. It's not the limit coming down. It's the target. 55 is our target speed. Where the limit is, well, that could be plus or minus 10, if not 15 miles per hour. So you have to consider that analogy and say to yourself, okay, 15, 13, 10 for the hypothetical system is a target. It's where we want to be. We can be cleaner, that's no big deal, but how much dirtier before we take action? And so what I always try and help impart to people is use the chart like I showed you, come up with your target. Now the way you set your limit is simply to go, flip there for me, 2 codes higher. So if 15, 13, 10 is your target, then 17, 15, 12 becomes your limit. And that's what you'd want your lab to alarm your samples against, or if you're taking them into your CMMS system, what you'd set your internal limit as. But don't set your limit and your target as the same value. You will be constantly fighting it. Because here's the big point. One of the key takeaways I have when I discuss the test is the accuracy of the test is pretty much give or take an ISO code already. So there's about 100 to 150% difference between any two results, meaning they can just about double between two readings on the same instrument. So the test has really got a lot of noise in it. So it's accurate to within about 1 ISO code. So you should give yourself a little bit more buffer than that. And that's my comment here, is that give yourself that 1 extra ISO code so that you know that if it changes by 2 ISO codes or more, now is time to take action, right? So if you're setting your target at 15, 13, 10, and you're at 16, 14, 11, that's pretty close to target. Don't worry about it yet. But once it hits 17, 15, 12, now we need to maybe consider the next steps, right? Inspect your breathers, add filtration, change your filters, whatever makes sense for your setup. But there we go. Hopefully you found that enlightening. You have a better understanding of ISO codes, so you know the terminology I've been using, and you have a way of identifying how to set a target, which then, like I said, lends itself to a limit. So with that, I will stop here and definitely thank everyone who's been on the line for participating, and hope you enjoyed it. If you do have any questions, my email is at the bottom, but I'll certainly take any questions that you want to throw into the chat now. Take a look here.
Yes. I'm not seeing any questions that came through the presentation, but Ahmed said, I like the way you've simplified the concept of oil cleanliness ISO codes. And I can definitely reiterate that It's always really, really helpful hearing, a presentation of something so complicated and something that's so technical. But myself, not being a practicing oil analysis technician, I can understand the concept and the procedure that is important for ensuring that it all goes smoothly. So I appreciate that as well.
Well, and like I said, I do know it's frequently misunderstood. Even those who think they know it don't really know it well enough to to use it properly. So it's one of those things where we always joke you know enough to be dangerous. So hopefully this helps people get out of that danger zone.
Yeah, that's amazing. No questions coming in, but I have one kind of logistical question.
Sure.
So this was part 1 that we went through ISO codes and setting targets. What does part 2 look like? Where do we go from here?
Part 2 is the 5th step that I went through at the beginning. It's kind of the tail end of this whole discussion. And how do we identify filters? How do we know how good a filter do we need? So understanding micron ratings, beta ratios, things like that to achieve our target, right? To aim for that target. So it's kind of the brackets of the big picture here. Where do we start and how do we end? We just left out all the middle.
Awesome. Well, I am looking forward to it. I'll connect with you offline and we'll go ahead and try and get that set up if you'd be so willing. I will give everyone one more second to stall for any other questions while we have Evan and his expertise on the line. If there's anything that you're wondering about either from this presentation or that he may be a good consultant on, please feel free to drop your question into the chat. If not, I hope everyone's Thursday ends out really well. And that everyone enjoys their weekend and joins us again next week for more conversations, activities, and webinars coming up. We have one question that just came in. I stalled perfectly enough. We have one question here from Ahmed that says, is it the responsibility of oil companies to supply clean oils? I love that question, Ahmed.
I really like that question too, because my short answer is no. And I'll give you 2 different perspectives as to why. Oftentimes people make this sort of same question as a statement, and they like the oil companies, they don't make our oil clean enough, or they don't, why did they leave behind those 2 teaspoons that we're talking about? And my joking answer always is they removed 99 point who knows what % of the dirt that was in your oil, right? Because think about where did crude oil come from, came out of the ground. So they've removed most of the contaminants. And so the point becomes, why do they not get out those last couple of teaspoons of material? So there's 2 answers to this. One answer is that in some ways they're fairly confident that if they did take it out, you'd probably just put it back in before you got the oil into the machine, meaning that through your general storage and handling practices that you'd recontaminate the oil to the point that you'd end up with those 2 teaspoons all over again. Second part of that statement, though, is also that they don't feel that those remaining 2 teaspoons are harmful enough that during the time from the moment you add the oil to your system cleaning it up to its original target or original operating cleanliness, that there'd be significant damage happening. So this is kind of, again, using the term, it's like the Pareto principle. They're basically saying that those last 2 teaspoons are the 20% of the problem, but would require 80% of the effort to get there. So from their perspective, they'd have to put a lot more effort to get those last couple of teaspoons out, and it really doesn't pay. So what you'll find is, short of a couple suppliers, because there are 2 that probably some people are quite familiar with, I won't mention brand names now, but there are 2 different oil companies who distinctly have programs that guarantee targets for how clean their oil is right out of the drum or the tote, whichever way you get it delivered. But anybody who knows dealing with those companies, you do pay a premium. So you go, yeah, why doesn't everybody hop on that bandwagon? Like I said, essentially it's not required. It doesn't make that much of a difference. It's up to the end user to get those last couple of teaspoons out, because they got other reasons to filter their oil. They got other contaminants getting in there than just the ones that came with the new oil. So long story short, no, it's not the oil company's responsibility. And if you try and make it their responsibility, you'll just end up having to pay for it. And it's usually cheaper to do it yourself than it is to get them to do it. So there's my longer answer.
Fabulous. Yes, Neil says that's the sweet spot between producing clean oil with cleaner oil to end user to decide it's marketable.
Mm-hmm.
Awesome. Well, thank you once again, everyone, for joining. Thank you, Evan, for a wonderful presentation as always. And I look forward to seeing everyone soon. Enjoy the rest of your day and your weekend. And see you all next time. Bye bye now.
All right. Bye.